Okay, so we are going to talk now about NMR, and this is probably one of my favorite methods. It's certainly very powerful. The author of our textbook says it is the most powerful method for gaining information, and I certainly agree. So we're going to talk about the NMR of carbon and hydrogen mostly, right, because we're studying organic chemistry. And let me remind you that NMR um, gives us insight with respect to the connectivity or the structure of a molecule because the structure affects how radiation interacts with the nucleus of the molecule, right? So this is really our main take home is going to be the connectivity of carbons and hydrogens. And we get that information because NMR is affected by connectivity, all right? So protons, let's just a little bit of background information now. Protons and neutrons in a nucleus behave as if they were spinning. This is something I do not entirely understand. It's way outside the scope of our course, but it's I think valuable for me to tell you this, that they act like this. So if you can think of a nuclei as if they're spinning, okay? Now, if an atom has an odd number of protons or neutrons, it's going to have a net nuclear spin. So since hydrogen typically has no neutrons, just one nuclear particle, that's an odd number of nuclear particles. Carbon-13 has an odd number of nuclear particles, okay? Nitrogen 15, fluorine, and so on, right? So an odd number of nuclear particles means that the nucleus is going to have some spin, right? Now, the spinning charge of the nucleus creates a magnetic field. That's why is that the case? Well, that's a physics question. I guess physics 2 usually does electricity and magnetism. But the spinning charge creates a magnetic field. So if I have hydrogen atoms, there's going to be a magnetic field around it, all right? So the magnetic field exists perpendicular to the axis of the spin, right? So this guy is spinning around like this, and the field is going to be perpendicular to that. Right, so what we do then is we take some sample, and if there's no magnetic field, the spins of these nuclei are just all over the place, all right? But as soon as we apply an external field, and this is our NMR apparatus, okay? As soon as we apply an external field, then the nuclei line up, right? So they either line up with, you see that alpha right there? They either line up with the magnetic field or against it. So this will be a high energy state of a spin will be against the magnetic field. They're either with it or against it. Now, as we apply the higher energy spin state is beta, right? And as we take, what we can do is we can take an alpha and we can apply energy to it and it will flip it to a beta, right? So this is a spin flip, right? Where it goes from alpha to a beta. All right, in this, I'm going to go slowly. I'm going to try to keep with the slides here because it'll keep me organized, all right? So we either have something with the magnetic field that is low energy state or it's against it, which is a high energy state. And that energy difference, by the way, is very characteristic of the environment that the nucleus is in. So when an atom with an alpha spin state is exposed to radio waves, with just the right energy, the photon is absorbed, and I think this arrow is supposed to be backwards. Sorry about that. The photon is absorbed, right? When we put this in a magnetic field, there's just a right energy is absorbed, and the spin flips to the beta state. The stronger the magnetic field, the greater the energy gap. All right. So, and the magnetic field is dictated by the environment. The magnetic field causes electrons to circulate. And so the more electrons there are around it, then the more shielded it is, okay? So nuclei that experience less of a magnetic field are said to be shielded, and they require less energy to flip. I'm not sure if I said that right a second ago. This is complicated, as you can see. So the nuclei surrounded by less electron density are said to be de-shielded, all right? And now the amount of energy necessary to flip depends on the electronic environment, and that's where we get our big take home, okay? Because we can, with our NMR apparatus, we can measure how much or how strong our magnetic field is that we're exposing a sample to. So when an alpha spins and are flipped to beta spins, energy is absorbed, and we measure that energy, right? And it's said to be in resonance, okay? This is a different kind of resonance than we typically think of with molecular orbitals, but it's said to be in resonance. That's where the NMR comes from, nuclear magnetic resonance, okay? The amount of energy required for each proton to spin flip tells us about its electronic environment, and every electronic environment is slightly different, and therefore we measure we measure the energies to flip them, and that tells us what the electronic environment is, okay? And thus the structure of the compound.